to Pomodoro Joe for Thursday, January 19th, 2023. Today we're looking at LeetCode problem 974, subarray sums divisible by k. It's a medium problem, and the problem statement says, given an integer array nums and an integer k, return the number of non-empty subarrays that have a sum divisible by k. A subarray is a contiguous part of an array. In our example, they have some array of integers, and k is equal to 5. And they return all of the subarrays that sum up to some number that's divisible evenly by 5. All right, so I'm going to try something a little bit different today. Hopefully this goes well. Start the Pomodoro timer now. 25 minutes on the Pomodoro timer and we'll get started. So with this one, we'll still have our result. We'll have some result that we return. And with the subarray, when you need to sum some subarrays, typically the brute force approach is something that works, but it's going to be an exponential algorithm, essentially calculating all of the subarrays sums and then finding out if they're divisible by k. It's going to take a long time. So when you sum subarrays, oftentimes you use a prefix sum. And a prefix sum is basically just keeping track of the total sum up to index I, and then if you need to find the sum of a subarray, you can just subtract one total sum from the other total sum. So you'll subtract the start index sum from the end index sum, and that will give you the sum of the subarray between the start and end indexes. Okay, so we can do something like have a total started at 0, and for every num in our nums, our total will increment by our num, and our prefix sum, we will append that total. And then I'm just going to print that out so you can take a look at it. So this is often how you would go about calculating a sum of subarrays. So we have 4, 5, 0, negative 2, negative 3, 1 as our input, and we go 4 plus 5 is 9, plus 0 is 9, minus 2 is 7, so on and so forth. So that's pretty straightforward. And if we want to calculate the subarray sum between any two elements, say these last two elements, we can just say, well, 5 minus 4 gives us 1. And if you look at that's right, it's 1. Okay. So that'll give us all of the information we need to calculate subarray sums using just a simple subtraction, but it doesn't give us what we need in terms of calculating the divisibility by k. What we need for that is actually something that I'll call a prefix remainder. And again, start it as an empty array. And here we're just going to say, okay, for every total, prefix remainder will be, let's see, let me append. It'll be the total modulo k. So that's going to give us the remainder of dividing total by k. And I'll print that out here so you can take a look at it, because that's kind of useful to see. All right, so here should be our prefix sum and then our prefix remainder. I'll give us a little bit more room. Okay, so we have our input array, we have our prefix sum, and then our prefix remainder. So this is going to be 4 divided by 5 gives us a remainder of 4. 9 divided by 5, remainder of 4. Another 9 divided by 5 is a remainder of 4. 7, 2, 4, 4, 5, and 0. Okay, so now we have all the remainders. How does that really help us? Well, the key insight here is to understand that whenever you look at two elements or two remainders in our prefix remainders, whatever delta there is between the remainders, that will be reflected in what we added in the subarray that lives in between those two remainders. Maybe I can describe that a little bit better by saying, if we look at, let's say this last one, we had some remainder of 4, and then the next remainder we have is 0. So something must have happened to bump this 4 either up to a 5 or down to a 0. Some change in the remainder happened to give us a new value for our remainder. So in that case, we just incremented our 4 to a 5 by adding 1, and we got a remainder of 0. Now what happens if the remainder doesn't change? That means whatever happened between this 4, this second 4 here, and this third 4, whatever happened in between those means there was no change to our remainder. And if there's no change to the remainder, that means whatever happened in between must be evenly divisible by our k, because it added 0 to our remainder. So that's the key insight. Whatever happens between two of the identical remainders, that subarray that happens in between there must be evenly divisible by our k. So between the first 4 and the second 4, we went from 4 to 9, and in fact, that's a 5, and it's divisible by 5. Between our second 4 and our third 4, again, we went from 5 to 0, or sorry, we went from total of 9 to 9, but we had a 5, we have a 0, again, that is evenly divisible by 5. Then when we go from 4 down to 2, all of a sudden we are at a 7 here, because we went from 9 subtracted 2. We're no longer divisible. We no longer have a subarray that's divisible by 5. But what about between these two 4s? That's where it gets a little bit more interesting. So we had a 9, we go down to 4. Well, 9 to 4, that's a difference of 5, which is also divisible by 5. So it turns out that for every pair of matching remainders, we have some subarray that is a multiple of our k. All right, so then all we need to do here is go through, keep track of how many of each remainder we've seen before, and anytime we have a pair, we can just add more subarrays to our result. And in fact, we add the number of remainders minus 1. You always have to have a pair. So if you had just 1, 4, for example, like this 2, if you just have 1, 2, there's no span that happened between two remainders of 2 to give us a new subarray divisible by 5. It's only when we have these like pairs. So 4 and 4, this 4, so this 4, this 4, this 4, this 4, this 4, this 4. Well, let's actually count this up. We should have 7 expected. So this would be 1, and then these 2 would make 2, 3, and then 4, 5, 6, and where's the 7th one? Well, it turns out the 7th one is this 0 itself. So the 7th pair isn't really even a pair. When the subtotal, or when the prefix sum itself is divisible by the value k, then we also have one subarray, the entire array up to that element. So we need to be special. We need to treat zeros a little bit differently than the others. So let's go through that. All right, we can clear out this. We'll keep these. We don't actually need this prefix sum. I don't think we're using it for anything, so we can actually get rid of that. We can get rid of it here too. Okay, but now we do need to keep track of something else. We need to have our remainder count. And that's just going to be some default dictionary for integers, where the key will be our remainder and the value will be how many times we've seen that remainder. And then so for every remainder in our prefix remainders, we can just say, well, our remainder count for that remainder, we'll increment it by 1. Okay, again, we had this one thing with our zeros though. We have to be a little bit careful with our zeros. Anytime we get a 0, we'll want to increment it by all the pairs of zeros, I guess. So even if, but with the exception of even if we just have 1 0. So even if we have 1 0, we'll sort of fake it out by starting our remainder counts at 0 equal to 1. That sort of means that we don't need that first pair. If we just get 1 0, that one itself should count. All right. And now we say, well, now if we have our remainder counts for our remainder, is that greater than 1? We have some pair. If we do have a pair, then we can increment our result by, and it turns out we can increment our result by the remainder count at that remainder, minus 1 because we still need to have the pairs. So for example, we've got 1, 2, 3, 4 4s down here. And so for the first 4, that's not going to count. Second 4, well, we have 1 span in between them, so we'll add 1. Third 4, well, we've got 2 potential spans. We've got 1 between the third 4 and the first 4, and 1 between the first 4, or the third 4 and the second 4. So that's 2 spans. So again, that's the number of remainders, matching remainders, minus 1. Okay, so I think that works. And at the very end, we return our result. We have our special case for zeros. Let's give this a shot. I'm a little bit nervous about this one. That seems to work. Let's submit this. Fair warning, I already submitted one of these earlier today that did pass, so hopefully this will still be passing. Oh, we have an unknown error. Let's try that again. Okay, I wonder what my unknown error is. There we go. Okay, so this does pass. It does okay. It beats 62% of other entries in terms of runtime. It beats 96% of other algorithms in terms of memory, which is actually really good. So there are things that we can do to improve on this. As I mentioned, or maybe I didn't mention this. There are things that we can do to improve on this. One thing we can do is we've got 2 for loops. One that goes through our nums calculating these prefix remainders, and then we go through the second time checking the remainders and counting them up. We could actually merge these into one for loop so that we don't end up traversing 2 different sets of values. We can just keep track of our prefix remainder here and do all these remainder counts. In fact, let's just give it a shot. I think there's a little bit of time left on our Pomodoro. Let's try that to see if we can make this work. So the first thing we need to do is we'll just move, let's see, we'll still need the remainder counts and the remainder counts at 0. So we'll move those up here. We don't need this prefix remainder anymore because we will be tracking that with our remainder counts. We'll still need the result, we'll still need the total. So instead of appending prefix remainder, we'll just have a current remainder equal to total mod k. So I'll just call this like remainder equals total mod k. And then we don't need that because we're going through the remainders already. And then the remainder count for that remainder plus equals 1. Yep, so we're keeping track of our remainders. I think this might be all we need to do. Let's try that out. That works. And let's submit that and see if that gives us any improvement. Whoa, that gives us significant improvement. This time we have a 96%, we beat 96% of other algorithms in terms of runtime. We only beat 87% in terms of memory, so for some reason we do a little bit worse in memory. I'm not sure why that is, but I would say that's still a pretty decent improvement. All right, I think we're out of time. Hope you enjoyed that. Hope you had fun. Hope you learned something. I'm working on my presentation style. I'm hoping to improve. So yes, feel free to leave some feedback. I know it's not great. I'm working on it. Trust me. All right, thanks for watching. Hope you enjoyed this. Hope you had fun. Write better code.